Hello, and thanks for clicking on this Nargilus production. Today, we are going to be talking about differential equations, the exponential model. So, differential equations are mathematicians' attempt to explain the world around them. And one of the models that we work with is the exponential model, which you've actually worked with before in both Algebra 2 and Pre-Calculus. Today, we're going to see how differential equations applies to that model and where it actually comes from, the formula that you use in Algebra 2 and Pre-Calculus. So let's get started. Okay, so first thing we want you to do is I'd like you to write the differential equation for the given scenario that's below. So we've done this before. It says the rate of change of population, rate of change in the population p with respect to time t is proportional to the current population. So the rate of change in the population p with respect to time t. Well, then that's a derivative dp dt is equal to, it's proportional. So it says proportional. That means directly proportional to the current population. So that's K times P, where K is your constant of proportionality, right? So that's the differential equation that we're talking about here that describes an exponential model, dp dt equals Kp. Now, what I'd like to do is I would like to go ahead and solve this differential equation. Now, you can do it because it is a separable differential equation. So let's go ahead and let's solve the differential equation dp dt equals Kp. So we are going to separate our variables. We're going to multiply both sides by dt, and then I'll divide both sides by p. Now remember, k is just a number. It's a constant of proportionality. So I'm going to keep the k over here on the right, and we'll set up what we have. We have dp over p is equal to k dt. Now, I could have taken the k and brought it underneath here with the value of p, with the variable p, but to be honest with you, it just creates more havoc than it's worth. When I'm done with this, I want to solve for p anyway, so I don't want to bring extra things over here on the side with p because eventually I'm going to have to move them back. So I might as well just keep the k where it is, and we'll go from there. So now we're going to integrate on both sides. The integral on the left, the integral of dp over p, is the natural log of the absolute value of p. The integral of k with respect to t is kt, and then we add the constant plus c. Now, our goal is to solve this for p. So to solve for p, we are going to exponentiate on both sides. We get the absolute value of p is equal to e to the kt plus c. We're still trying to solve for p. This doesn't say p. It says the absolute value of p. So we're going to have to use that definition of absolute value that we know so well. The definition of the absolute value of p is equal to p. If p is greater than or equal to 0, it's equal to the opposite of p if p is less than 0, which means that the absolute value of p could be positive p or it could be negative p, depending on what the value of p is. So we have to consider both here because we don't know what the value of p is. And that's equal to e to the kt plus c. Now we want to solve this for p. To do this mathematically, what we do is we take the right-hand side and we split it up through multiplication, because if I multiply the same bases, it would involve adding their exponents. So these two steps are equal to each other. And now what we're going to do is we're going to take this plus or minus and we're going to stick it on the e to the c, because e to the c is just some number. So we're going to stick it there with that constant. And we are going to say p equals e to the kt times plus or minus e to the c. And then I'm going to rename plus or minus e to the c with a different letter. I'm going to let a equal plus or minus e to the c. So we get p equals a e to the kt power. So this is the correct solution, but now I'm going to take it one step further. If t equals 0, then p is really the initial population, right? Because it's the population at time 0. So if I let t equals 0, then p is really the initial population p naught. So if I substitute that in, I would get p naught is equal to a e to the k times 0. So p naught is equal to a e to the 0 power. E to the 0 is 1. So then p naught must be a, which means that my equation that I use is p equals p naught e to the kt power. And this is the one that you saw back in Algebra 2 and pre-calculus. It's the one that we've used before for exponential growth, exponential decay, as well as half-life, all those kinds of things. So that's the one we're going to use here. That's where it comes from. It comes from this differential equation that we have written. So let's take a look, just a review here. Here's our exponential growth model. P equals P naught e to the kt. P represents the amount after some time t. P naught is the initial value or the initial population. K is that constant of proportionality. If you're solving a differential or you're solving this for this equation, this is the first thing that you need to know. You need to know what K is to be able to play the game. T represents the time. If k is greater than 0, it represents exponential growth. And if k is less than 0, it represents exponential decay. All right, so let's see how you can use this differential equation. Look, basically what we want you to be able to do, first of all, is this. If I give you, or someone gives you on the exam, dp dt equals kp, you immediately should understand that p equals p naught e to the kt power. You don't have to prove it to me or derive it for me like we just did on the previous slide. You can just assume that that's true. So if I say, hey, dw dt is equal to kw, then you know automatically w equals w naught e to the kt. That's the equation that you would get if you solved it. Okay? And then that would be the equation that you'd use to work out your problem or whatever it may be. All right? That's the first major thing you need to be able to understand here. Okay, so now let's find the particular solution if dp dt equals 5p and p equals 30 when t equals 0. So I know dp dt equals 5p. Well, I already know that if dp dt equals kp, then that would mean that p equals p naught e to the kt power. That's the formula that we just came up with. So then dp dt, if it's equal to 5p, then p is equal to p naught e to the 5t power, because k is just 5 now. Okay? And then p equals 30 when t equals 0. So there's two ways you can think about it. When t equals 0, p equals 30. That means the initial population is 30. So that would give you then p equals 30 e to the 5t power. Or the other way you can do it is you have a point, t equals 0, p equals 30. Plug it into this equation here, and you could solve for p naught. You could do it either way. It does the same thing. So you'd have 30 equals p naught e to the 5 times 0. 30 equals p naught 5 e to the 0. E to the 0 is just 1, so p naught is 30, which either way gives you this equation. P equals 30 e to the 5t. So you can just solve this straight away without having to derive the fact that dp dt equals 5p gives you p equals p naught e to the 5t power. You can just do it one shot and be done with it. All right, let's try one more here. The rate of change in a population p is proportional to the population at time t in days. Oh, well, that's the differential equation that we started with. So dp dt is equal to kp. That's what that's telling me. At time t equals 0 days, the population is 500 people. So when t is 0, p is 500, which means that p naught must be 500. At time t equals 10 days, the population is 1,200. Okay, when t is 10, the population is 1,200. They want to know at what time t is the population 800. So what's the value of t? Well, if we know the differential equation dp dt equals kp is the differential equation we're working with, then we know p equals p naught e to the kt power. We know p naught is 500, so p equals 500 e to the kt power. Now, to be able to play the game, to figure out when the population is 800, I would need to know what k is, what the constant of proportionality is. I could figure it out because I know when t is 10, P is 1200. So I can just substitute them in. 1200 equals 500 e to the 10k. Now I'm going to solve this for k. So to do this, it's all Algebra 2 pre-calculus. You're going to divide both sides by 500. You get 12 over 5 equals e to the 10k. Now let me come up here. 12 over 5 equals e to the 10k. I'm going to take the natural log on both sides because I need to get the power down. I can't solve for this with the variable up here. So that would give me the natural log of 12 over 5 equals 10k ln e. But ln e is 1. So the natural log of 12 over 5 equals 10k. And I divide both sides by 10. I get k equals the natural log of 12 over 5 all over 10. So that's what k is. So now my equation looks like this. P equals 500 e to the natural log of 12 over 5 over 10 t. And now I want to know what the population I want to know how much time it takes for the population to be 800. So I'm going to put 800 in. 800 equals 500 e to the natural log of 12 over 5 over 10 t. All right, so now I'm going to solve this for t. Divide both sides by 500. You have 8 over 5 equals e to the natural log of 12 over 5 over 10 times t. Take the natural log on both sides. You have the natural log of 8 over 5 equals the natural log of 12 over 5 over 10 times t. And then you can multiply by the reciprocal of this to get t alone. It's a disaster, but I mean, it'll work. Multiply by 10 over ln 12 fifths on both sides. 10 over ln 12 fifths. So we don't have a calculator, so my answer is just 10 ln 8 over 5 over ln 12 over 5 is equal to t. You could type that in the calculator and it would give you the answer. Sometimes on the exam, they give you the exact answer just like this, and they expect you to give them that response. And that's it. That's all there is to this. So this is our one example of an exponential or a differential equation model that we're going to work with this year. There are many, many, many others of which you will see throughout the rest of your calculus journey through the years. But this is the very first one. An example of something you saw in Algebra 2 and pre-calculus, didn't really know where it came from, but now you do. As always, thanks for clicking.